All right, so we're going to talk about rotational dynamics and how to solve problems involving rotational dynamics. So a lot of these steps will essentially read the same as what we did in linear dynamics, except for we're going to add in the variables and concepts related to the rotational aspects. So the first most important thing is that you need to model the object as some sort of simple shape. Unless it's impossible to model it as a simple shape because they're asking you to experimentally determine the inertia from experimental means because the object is intentionally wonky. We're going to look at an example over here where we have a telephone pole. So we can model that telephone pole as like a long, thin rod. Like that would be a good assumption to make. So we're going to need to identify coordinate axes. Those coordinate axes will include the axis of rotation. So sometimes the axes will be in X and Y. Sometimes you might just look at parallel and perpendicular. It'll depend on what's going on. So for example, in this problem right here with the telephone pole, we are going to be looking at essentially the angular acceleration as it's falling. And it's wanting us to estimate the pole's angular acceleration when it has fallen by 25 degrees from the vertical. So as I go to identify my coordinate axes, the first thing I'm going to realize, well, the vertical is important, so I should probably draw that in here. I've also got a horizontal. I don't know if that'll be needed, but I'm going to kind of define my coordinate axes here. And it wants the axis of rotation to be about the part still connected to the base. So I'm going to make that axis of rotation essentially this point right here where it is still kind of in contact. So that is going to be my axis of rotation. So I've kind of set up a coordinate system there. If I wanted to, I could define like the positive X direction and I could define the positive Y direction if that was of use. We want to list the variables that were given. I usually do that by drawing on my diagram. I didn't draw a super big diagram here, so it'll be a little more difficult for me to label. I usually try and draw larger diagrams, but I wanted to have the steps on the board as well as the examples so we could kind of work those side by side. So if I go through and read, we have a 7-meter tall telephone pole. So I'm going to assume that this length here is the 7 meters that it is referring to. And that's basically like the length of the rod. And it's going to have a mass M, which is equal to 260 kilograms. And the 25 degrees, that's really all they give us. And we are looking for an angular acceleration at this instant in time. So I am looking essentially for that alpha, that angular acceleration when it is at that 25 degree orientation. So I should probably label that 25 degrees here as my angle theta. So because I'm going to treat it like a long thin rod, I'm going to assume that the thickness here doesn't actually matter. So I can just pretend like this is just a line. So that's the nice thing about the long thin rod. So I've listed my variables, figured out what I'm looking for. I'm going to identify the forces and lever arms. So there are several forces acting. So the first force that's acting is obviously going to be that force of gravity. That force of gravity we are going to assume acts straight down. And we assume that it acts at the center of mass of the rod. So I am going to assume this is a uniform rod, so the center of mass of the rod is going to be dead in the center. So that distance is going to be L/2. So I like to add those lever arms as we go. Identify a force, identify the lever arm, because that's my axis of rotation here. So if I were to actually draw that lever arm as a vector, that would be there. So that would be the lever arm R. Now that is not actually the only force acting. There is additionally going to be a normal force because this rod is actually resting on its base. So there is going to be a normal force. So the center of mass of this rod is going to fall. So the gravitational force does need to be larger than the normal force in order for the center of mass to get lower. The normal force, though, is acting at my axis of rotation, so it is not going to exert any torque. So in this case, when we're looking at rotation, the only force that's contributing to torque is going to be that gravitational force. So I need to determine the direction of torques. In this case, if there is only one, but if I want to show you, I can do the right hand rule. So I put my fingers in the direction of R, rotate my palm towards F, and I can see, just like I had thought here, that that is going to cause a torque that is in the counterclockwise direction, which I could assume to be positive. But even if this, because there is only one torque, I can always just call whatever direction it's rotating positive. So if they don't specifically define clockwise or counterclockwise, or they don't give you a picture and you have to draw your own, you can always just assume that the direction that it's rotating is going to be the positive direction. So that's my label diagram. That's essentially everything I need to do to solve this problem. So I'm now going to apply Newton's second law for rotation. So my net torque, in this case, is going to be the sum of all of the torques that I have. Well, in this case, that's only going to be the torque due to gravity. So I'm going to write the torque due to gravity here. That is positive, so I'm just going to leave that as a positive. And then that's going to equal I times alpha. If I had multiple torques, I would write multiple forces. So for example, if I chose a different axis of rotation and there was torque by normal force, I would do the torque by gravity minus the torque due to normal force is equal to I alpha. So just like we would write net force equations with maybe gravity minus normal force is ma or something along those lines, I can write net torque equations the same way. But in this case, I only have to worry about the torque due to gravity. So that torque due to gravity is going to be based on F perpendicular times R. So that's going to be FG perpendicular, and that is going to equal I times alpha. Well, if I'm going to assume this is a long, thin rod, then the moment of inertia of a long, thin rod is going to be about that end point is going to be the 1/3 ml squared. What about this perpendicular component of gravity? Well, I know that this theta right here is 25 degrees, which means that this theta right here is also 25 degrees. So that my theta is there as well. So if I wanted to find the perpendicular component of my force to my lever arm, it would be that component right there, which would be based on sine theta. So I can write that my gravitational force perpendicular is going to be mg sine theta. And then in terms of my coordinates, that's going to be at a lever arm distance of L over 2. So actually I can see here, very fun, that the mass of the rod actually cancels out. So they gave it to me, but I don't need it. So it didn't matter what the mass of this rod is to find the angular acceleration. I do notice that one of the L's also cancels out. So if I wanted to solve for alpha, I am going to end up with, let's see, multiplying by 3 g sine theta times L. No, L's going to be on the bottom. Divided by 2 times L. So that's going to be my equation for the angular acceleration. So one thing that I notice is that this is dependent on the length. It's not specifically dependent on the mass, but it's dependent on the length because that's determining essentially where the mass is located. So that if this was a longer rod, that center of mass would be higher. So if it was a longer rod, you would have more torque due to gravity. The other thing I noticed, it is dependent on the acceleration to gravity. So if it was on the moon, I would have a smaller angular acceleration, and it's dependent on the angle theta. So if I think about this, at 25 degrees, I'm going to have a particular value for my angular acceleration. But what about as it keeps falling? Am I always going to have the same angular acceleration? Well, no. The length of the rod is always going to stay the same. The acceleration due to gravity is going to stay the same as it falls, but that angle is going to change. For example, if that rod was horizontal, so it gotten to the point where the rod was horizontal and you've got your gravitational force here, and you've got your lever arm there, well, that theta is going to be 90 degrees. So as this thing falls, the torque is actually going to increase and the angular acceleration is going to increase, which means it's going to be speeding up as it falls, but it's going to be speeding up at a faster and faster rate. So if we actually were to then solve this problem, now it's just a matter of plugging in numbers. So 3 times 9.8 meters per second squared times sine of 25 degrees over 2 times L, which is 7 meters. You should calculate out to approximately 0.89 radians per second squared. All right, in this case, there's an engine and a small airplane, and it gives us a particular amount of torque that engine can supply to the propeller. It's a single blade propeller. It tells us that it's 2 meters long. We have 40 kilograms single blade, and then we want to figure out how long does it take the propeller to reach 2,000 RPMs. So going through kind of our steps, we want to model the object as a simple shape. So they did give us a picture of this propeller, and they tell it's a single blade propeller, so which means it's giving us a hint that this is going to be treated as a single unit. So I can actually simplify that down and treat that as a long, thin rod rotating about its center, so that the center axis is coming here so that the blade can spin in the plane of the page, but the axis of rotation is in and out of the page. So that is a 2 meter long propeller. I'm going to call that L. And it is going to have a mass here of 40 kilograms. And it tells us that the torque that can be supplied is going to equal to, let's see, 500 Newton meters. And we're looking for how long does it take to reach 2,000 RPM. Well, what is RPM? That is revolutions per minute, so that is an angular speed. So that's giving us a final angular speed of 2,000 RPM. So I've modeled the object in a simple shape. I've identified my coordinate axes. I've listed my known variables. I'm identifying what my unknown is. And then I want to identify any forces and lever arms. Well, actually, in this case, they don't really tell us anything about the forces. Now, the gravity is going to act on this blade. They do give us a mass, so there is going to be a force of gravity pointing straight down. But that's going to be acting at the axis of rotation, so it can't supply torque. There's also going to be a normal force being supplied, because that blade's going to be resting on the axle, so that's why it doesn't fall to the ground, is because the gravitational forces, the normal forces, are going to be balanced, but neither of those are going to exert any torque. The torque is being caused essentially by the propeller mechanism, the engine mechanism, whatever that is attached, which we don't know anything about. So there's not really much to do in terms of the forces and lever arms, because we already know the torque. Because the torque is known, we don't actually need to break the torque and forces up. So I don't really need to do any of this here. So I can skip right to applying Newton's second law for rotation. So I can write that my net torque is going to equal I times alpha. And I'm going to assume that my net torque is a known value, and that's just going to be T. And then for my moment of inertia, I'm going to assume that this is a long, thin rod, and it's being rotated about its center. So a long, thin rod about its center is going to be 1/12 ml squared. And then we have alpha. The problem here is that it's asking me for time, and Newton's second law for rotation doesn't involve time. So this is where we have to come back down. We've used a moment of inertia formula, so I'm going to need to maybe employ some rotational kinematics. So I'm going to assume that this thing starts at rest, so omega 0 is 0. I know that my final angular velocity is going to be 2,000 RPMs. I'm looking for time. So what I can do here is I know torque, I know mass, I know length. I can actually solve for angular acceleration and plug it into a kinematic equation. So angular acceleration is going to be 12 times my torque over ml squared. And then what kinematic equation could I do? Well, when I know initial velocities and final velocities, and I'm looking for time and I have angular acceleration, this is just the basic one. Omega equals omega 0 plus alpha times t. So I'm looking for time. Omega 0 is 0. So if I solve for time, I get time is going to be omega over alpha. So if I sub in for omega over alpha, that's going to basically flip this over. So I'm going to get omega times ml squared over 12 times the torque. And I'm going to call that omega F because that's what I defined it up here. So if I plug in, I'm going to end up with a 2,000 RPMs. Well, that's not the right units. So let's go. Say, all right, 2,000 RPMs. That's 2,000 revolutions for every 1 minute. So 1 revolution is 2 pi radians. And 1 minute is 60 seconds. So let's see. Minutes cancels minutes. Revs cancels revs. So that's radians per second. So that's right. So omega F is going to end up being 2,000 times 2 pi divided by 60 radians per second. The mass is 40 kilograms. The length is 2 meters, and that's squared. And you divide by 12 times 500 Newton meters. And we plug that one in, we get 2,000 times 2 pi divided by 60 times 40 times 2 squared divided by 12 divided by 500. Gives me about 5.6 seconds. So conceptually, if I look at this equation, basically if I have a larger amount of torque, then it's going to take a shorter amount of time for this to reach speed. So that makes sense. The same is true with car engines. If you want to have a really fast racing car, you need to have a high torque engine. The longer the propeller is, the much larger time is going to be. So that's going to contribute your moment of inertia here. So if this is a really long propeller with that particular torque, you're going to have more resistance to rotation, so it's going to take a longer time. Same with more mass. If there's more mass, there's more inertia, so therefore it's going to take longer for it to reach speed. So, like I said, these are 2 examples that involve pure rotation. Tomorrow we're going to look at pulleys. Pulleys involve both linear and rotational motion.